Hi everyone. So in this lecture we're going to talk about some of the important aspects of applied biostatistics, and in particular we're going to talk about some issues involving sample size, randomization, why that's important, and what you need to do to adjust for multiple hypothesis testing. Okay? So sample size. So sample size is a critical component, and it's one of the most critical components in order to determine whether or not a study has a chance of being successful or not. The sample size has a profound effect on whether or not the study is going to reach statistical significance. And members of committees like RBs, study sections, etc., are going to pay close attention to sample size calculations and how those calculations are performed anytime you propose a study. And these kinds of committees are usually going to ultimately determine whether or not a study is funded, for instance, if it's NIH, or whether the study can move forward if it's the IRB. So these committees are going to try to understand and gauge whether or not the proposed sample size is sufficient. And so what exactly does that mean? Well, what that means is, does the study have a remote chance of proving the claim that you're trying to prove with the study? Okay, so it turns out, and an important point is that it's usually unethical to conduct a study on humans if it has no hope of being successful. So if you have absolutely no chance of detecting the kind of difference that you hypothesize you're going to see, for instance, between a placebo and a treatment group. So what can happen is, if you don't have a sufficient sample sizes, that your results may appear to be clinically meaningful. So for instance, you may observe an odds ratio of 2, so that would be a clinically meaningful odds ratio. It would essentially mean that the odds of some event is twice that, depending on whether you're, say, in a exposed group versus an unexposed group. So even clinically meaningful in large effect sizes like this, you wouldn't be able to reach statistical significance if your sample size is too small. So case in point, there was a study here done here, and looked at 71 negative random controlled trials of new therapies published in prominent medical journals. And essentially the conclusion were that the sample sizes were too small to provide a reasonable assurance that a clinically meaningful difference would not be missed or could be detected. Okay, and in fact, in 75% of these studies, the sample size was so small that you didn't even have a reasonable chance or reasonable assurance to detect up to a 50% improvement. Okay, so these kinds of studies are essentially failed from the start, doomed to failure from the start. Okay, so some intuitive questions that you can ask yourself at this point to kind of start thinking along the lines of what influences sample size are as follows. So what sample size, large or small, would you need if there's a very large variance in the outcome that you're interested in? For instance, systolic blood pressure, just as an example. Okay. Another question: what sample size would be needed if the investigator wanted the answer to be extremely close to the true value? For instance, if they wanted a very narrow confidence interval. So for instance, they wanted a confidence interval that was very precise and was most likely to contain the true value. Another type of question, intuitive question, is what would happen to the sample size if the difference that the investigator is trying to detect was extremely small? So for instance, let's just say you have a treatment group and a placebo group, and you're interested in an event type of outcome, so death versus not, in the two groups, and the rate of death in the treatment group is 0.45, and the rate of death in the placebo group is 0.5. So would your study be able to detect this difference of just 5%? Okay, so your intuition should tell you that in all three of those above cases, it's going to require a larger sample size. Okay. So in more detail, what are some factors that influence sample size? So for instance, whether you have paired versus unpaired data. So if you have paired data, typically what happens is the intra-subject correlation can be exploited and is exploited, and that typically leads to a reduction in the overall sample size versus if you have unpaired data. Okay. Another important thing kind of that we've alluded to on the last slide is whether you have a large or a small variance in your outcome. So the larger the variation is in your outcome, naturally the more the larger the sample size is you're going to have in order to be precise with confidence intervals or any kind of estimation of say a mean. Okay, another important factor or factors that influence sample size are beta, and remember we've defined beta on a few slides ago, and that's the probability of a type 2 error or the probability of a false negative. Okay, so that would essentially mean so a type 2 error would be you didn't detect the difference between, say, a treatment and a placebo group, but there really is a difference. Okay, so that was one, remember, type of error. Sample size is also influenced by alpha, naturally, which is your probability of a type 1 error or a false positive. So if you decrease these probabilities or if you decrease these chances of making mistakes, naturally you're going to have more information. So you're going to have larger sample sizes. Okay. Another factor influencing sample size is whether you're doing a one-tailed or a two-tailed test. Okay, and then finally, another key factor that influences sample size is whether or not your effect size is small or large. So if you're trying to detect, as in the previous example I talked about, a 5% difference, that's going to require many more subjects than if you expect that the difference between your two groups is, say, 20%. That a 20% difference in the occurrence of an event between two groups will be much easier to detect with a lower number of samples. Okay, lower number of observations. Okay. So how do we get at this sample size and kind of get some more intuition about it? Well, one thing we can do is kind of start out with this naive sample size derivation, and this thing is in your book, and it basically starts out with looking at a paired t-test. Okay, so if we were looking at a paired t-test and we were trying to determine, when would we reject H naught. So remember, if we reject H naught, that means that we have found a difference. Okay, typically studies are designed because the researchers have in mind that there is some kind of difference. Okay, and we would want sufficient sample size in order to be able to detect that difference, or in statistical terms that would mean to reject this H naught. Okay, so if we're talking about the paired t-test, then how would we reject H naught? Well, basically what would happen is our test statistic, if you remember, which is this D bar. So remember, D bar was the average of the differences divided by the standard error. If that quantity is too large, and I've swapped up a little bit of the notation from your book because I don't think that your book is 100% accurate with this notation that they're using. They're writing T sub alpha here, but that's not technically correct, okay? Because depending on whether you're doing a one-tailed or a two-tailed test, sometimes it'll be T alpha, and if you're doing a two-tailed test, it would be T alpha over 2, okay? So I'm being general here. I'm saying T sub C, and this T sub C is supposed to correspond to the value on the T distribution that starts the rejection region. Okay, so let me just draw a very small graph out here. And if I drew the T distribution, remember it's going to kind of look normal, but it's going to have fatter tails than the normal distribution. So this T sub C would be whatever point out here on the t-distribution that would lead me to reject H naught if I were to observe my test statistic out here. So that would be your extreme type of event. Okay, so we would reject the null hypothesis if our observed t-statistic or our data were too extreme, and that would be and that's what this indicates, that statistic is larger than some t-value. Okay, and I've written here in this bullet, this t sub c denotes the boundary of the rejection region. Okay, so that's the point, that if we were to see our test statistic outside of that range or larger than that, we would say, hey, this we should reject H naught. This what we observed is too extreme under H naught. Okay, and remember, d bar is the mean of the differences, and S sub d is the sample standard deviation of the differences. Okay, so for a two-tailed test, I have here this critical point, this z sub c, would be 1.96. Okay, it's not too important that you remember that, but just understand that, that's why I essentially changed the notation that the book's using. Okay, if we were doing a two-tailed test, and in both of these situations, alpha is our default value of 0.05, so we have a 5% chance of making a type 1 error. Then our t-value, our z, our critical value is 1.64. Okay, so it's essentially what we're going to do is eventually we're going to replace this t sub c with these z's, and the reason is because at the moment this t sub c also depends on the sample size. Okay, so this t sub c also depends on the degrees of freedom, which involves n. So we want to solve this thing for n, this inequality for n, and come up with something that tells us what sample size n do we need in order to be in this rejection region, in order for us to reject H naught and conclude that there is some difference between groups, say. Okay, and that's what I've written here. So essentially all I did, or all the book did, was replace t with z. And if you just keep in mind that if your n is large, the t-distribution is approximately equal to the standard normal distribution. So that's why it's appropriate to replace this t at this point with the z. Okay, so all I've done here is replace that with a z sub c now, and solved for n. Okay, so if you were to go back here, let me take some of this away. If you were to go back here and you replace this guy with z sub c and solved for n, then this is the formula that you would come up with. Okay, this is kind of a naive derivation, as I've mentioned in the slide title, because it doesn't really take into account a type 2 error, and your book illustrates that in a table that I'm going to show in a minute. Okay, so this is a naive derivation, but it kind of gives us some intuition about what this eventual sample size formula is going to look like. Okay, but again, remember, this derivation is not the one at the end of the day that you're going to use. It's essentially equivalent to 50% power. Okay, this formula here is essentially equivalent to a 50% power. So you have a 50% chance to detect the difference if you use that formula, and that's generally not acceptable. Okay, typically for most funded studies, you need at least 80% chance. So you have to have some reasonable chance of finding significance. Okay, so that's what I have here in this second bullet. So it says this formula and others in the book that say something like considering alpha or type 1 only, they're equivalent to having 50% power. So you only have a 50% chance to detect a difference, this kind of difference d bar. Okay, and in most cases this is not going to be acceptable. But however, the derivation is the useful first step in understanding how the sample size is computed. Okay, so some important points that we can look at and kind of gauge, and if we look at this formula on the previous slide, this kind of naive formula, we can get an idea of what happens as certain things change. So for instance, if we increase s squared, or s, so if we increase our sample standard deviation, that's up here in the top of this. Let me remove some of this so we can get a better picture. So this is in the top, in the numerator of this quantity. So if we increase that, then naturally, so if we increase s, then naturally n is going to increase. Okay? So, and intuitively that makes sense, because if we increase our uncertainty, then of course you should expect that we need more sample sizes. We need more observations in our sample to overcome that increased uncertainty. Okay? And if we look at the formula for the sample size here, if we look at this z quantiles, we can kind of get an idea of what happens if we change our alpha level as well. So if we change our probability of a type 1 error, so if it's 0.05, then the value that we should be using for z sub c is 1.96. You can look that up, and it's not important to know this exact number, but you can look that up in a table for the standard normal distribution if you wanted to. Okay. Now, if we instead set alpha to be 0.01, then the corresponding z that we would need to use is 2.58. Okay, so after we square both of these quantities, remember there's a square here, so it's not just z, it's z squared in the formula for the sample size. Look what happens to our overall number just by merely going from a 5% chance of a type 1 error to a 1% chance. That nearly doubles our required sample size. So this is almost a doubling of the required n if we go just from a 5% chance of a type 1 error to a 1% chance. Alright? Well, another thing we can kind of gauge by looking at this formula is what happens if d bar becomes large. So remember, d bar is the difference that we're trying to detect. So d bar would for instance be the difference in, say, systolic blood pressure or mean systolic blood pressure between a placebo and a treatment group. Okay, naturally if that difference becomes large, then it should be easier to detect, right? So in fact, n gets smaller if the difference that we're trying to detect gets larger. So large differences require less sample size to detect, and you can immediately see that from the formula, right? So we're dividing by something here, this d bar squared. If we increase that, so if we increase the denominator, our n gets smaller. So as d bar increases, that leads to a decrease in n. Okay. So now I want to talk a little bit about, what's the difference between clinical and statistical significance. So clinical significance indicates whether an observed difference is clinically meaningful or clinically important. So let's look at two examples. So you've got a new treatment for hypertension, and it reduces systolic blood pressure by 2 to 3 millimeters of mercury. Okay, some might argue that, yeah, there's a 2 to 3 millimeters of mercury change, but that probably not clinically meaningful. It's such a small change. Okay, however, bullet 2, if you've got a new treatment for pancreatic cancer and it increases 5-year survival by 10%, most would probably argue that that's a clinically meaningful increase in survival. So the rate has jumped by 10%. Okay, so the point is, statistical significance is a statistical construct. All it means is that there is a small likelihood that the difference we observed occurred by mere chance. Okay? So in both of these examples that I've pointed out above, so both of these examples, if you were to do a study and you had a large enough N, then you may reach statistical significance in both of those studies. So if you had a huge number of individuals in the study, in the treatment group and in the placebo group, and you did the comparison, you may wind up showing that a 2 to 3 millimeter of mercury difference in systolic blood pressure is statistically significant just because you had so many individuals in your study. But whether that's clinically meaningful or not is another story, and it's important to think about the differences between those two when you're thinking about doing a study or when you're reading an article, whether what they've reported means anything clinically. Yeah, it may have reached statistical significance. For instance, you may have had an odds ratio of 1.1, and you may have gotten a p-value that's less than 0.05, but what does an odds ratio of 1.1 really mean in terms of whatever the clinical problem is that you're studying? Okay, so the point is, sometimes you can have statistical significance, but clinically it means nothing. Okay. Okay, so let's do just a refresh of some of the things from a few lectures ago about beta and type 1 error, because this is important. This is the important part whenever we're talking about the power of our study. So recall that beta is just some thing, we've just chosen this beta symbol because we need a symbol different from alpha, because we're talking about a different type of event that we want to describe the probability of. So remember, beta was the probability that we commit a type 2 error. So a type 2 error is a false negative. So there's a true difference, but the study result's not statistically significant. So you don't want to miss that. Okay? And the power of a study is essentially just 1 minus this beta. So 1 minus beta is equal to the power. So the power of a study is essentially just the probability that you detect a true difference. Okay? So if you remember, the default choice in most of your medical literature for alpha is 0.05. So remember, alpha and beta are describing two different things. Alpha is the probability of a type 1 error, so that would mean we're making a false claim that something's going on when it really, in fact, isn't. And we set that from the start to be small because we want to guard against that. Okay? And often a default power is also set at 80% for a lot of different situations, but this really isn't as set in stone as the alpha equals 0.05. Sometimes studies can be powered at 80%, 85%, 90%, and you can probably intuitively tell that the more your power increases, the more sample size you're going to have. Okay? But rarely is this power set below 0. So most of the time your funding agencies are going to require a minimum of 80% power. So you should at least have an 80% chance that your study is going to detect some kind of difference. Okay? So here's a table from the book. I'll zoom in a little bit on it. And this table from the book gives you some of the sample size formulas in different situations. And remember, these first two are really just kind of naive demonstrations, and those are the sample size formulas that you would get if you're not thinking about power at all. So essentially, in both of those formulas, your power is 50%. So the chance of your study being successful if you use those sample size formulas is like flipping a coin. It's 50-50. Okay, and the reason is because it's missing in here the z sub beta part that you see in this formula and in this formula. Okay, so if your probability of a type 2 error is set to be 50%, then this guy right here would be 0. And that's why these first two formulas are equivalent to having a power of 50%. Okay, because at a power of 50%, these z values, again, would be 0. Okay, so let's take this away. So if you're doing, if you're going to use a student's t-test, so that would be where you, for instance, have a trial and you have an experimental group and a control group, and you're looking at a continuous outcome, say systolic blood pressure or diastolic blood pressure or something like that. This would be a valid formula to use for your sample size. If you're looking at testing the differences in say, two proportions, so you have an event, for instance, death, in your experimental group and your control group, and you're interested in comparing the rate that these events happen, then you could use this sample size formula in order to figure out how many people, how many participants that you need. And these n's, so there are some important things going on in this table, and one of the important things is an assumption that both your groups, so your experimental group or your treatment group and your placebo group or your control group, are the same size. Okay, and these n's give you the sample size in each group. Okay, so if you wanted to know the total, then you would need to multiply that n that you get from this formula by 2. Okay. So let's look at an example, just to kind of see the mechanics of how this thing works out. So you've got researchers, and they're going to conduct a randomized controlled trial for a hypertensive drug. You're going to have one treatment group and one control group, and the measure is going to be systolic blood pressure. So the researchers believe, and it could be from pilot data or it could just be from expert knowledge, so they may know something about the pharmaceutical properties of the drug, and they may have these expectations, but at any rate, they estimate that they're going to see this. So they estimate that their sample standard deviation is going to be 15 millimeters of mercury, and they expect that the treatment group and the control group are going to be different by 10 millimeters of mercury. Okay? So actually we should probably, this kind of wouldn't make sense how it's written right now, we should probably write it like this: X bar in the treatment group minus X bar so X bar in the treatment group so we should probably, this actually makes more sense. So let's switch these two around. So this is actually what they expect to happen. They expect that the mean systolic blood pressure in the treatment group, in the placebo group or the control group, is going to be at least 10 millimeters of mercury greater than in the treatment group. Otherwise, why would they do the study otherwise, if they expected that you were going to have a higher blood pressure in the treatment group, right? So that's why I've rewritten this. How it's written right now wouldn't necessarily make sense. They wouldn't even be interested in conducting the study if they found that the blood pressure in the treatment group was in fact larger than the blood pressure in the control group. Okay, if this is a study trying to decrease blood pressure. All right. So just keep that in mind. This should be the correct. It's not going to change our formula, because essentially what we're going to do is, at the end of the day, is we're going to square this difference. So we're going to wind up squaring this guy. Okay, so they're going to perform a two-tailed test. They're going to set alpha to 0.05, which is the convention in the literature. And they want 80% power So what this translates to is if you use the formula, remember, power is equal to 1 minus beta. So in other words, beta would be 0.2. So they only have a 0.2 or a 20% chance to commit a type 2 error. Or in other words, they have an 80% power to detect this difference. So that's what they're aiming for. Okay, so systolic blood pressure is a continuous measure, and in order to calculate the sample size, we're going to go with this formula for the T. So we'll go back. We're going to go with this formula here. So let's look at all the pieces that we need in order to put this formula together and carry out this computation. So if we use that formula, this is the formula for N. And let's just see what happens when we plug everything in. So if our alpha is 0.05, then I've already said on a previous slide that our Z sub C is going to be 1.96, so I have that here. Alright, take this away. If we want 80% power, in other words, beta equals 0.2, then this Z sub beta piece here turns out to be 0.84, and that's in your book. If you want a different level of power, then you just need to figure out what beta is and find the appropriate value, this Z sub beta, on a standard normal table or standard normal software that gives you quantiles for the standard normal distribution. Okay, so let's take these away. So that's this first piece in the numerator. The second piece that we need is this estimated standard deviation, and from their analysis or from their pilot data, they estimated or expect that that's going to be 15. Okay, so that's what is here, and it's squared. Okay, and then finally the difference that they expect to see. So they're expecting to see a difference of 10. So they expect the mean systolic blood pressure to be different by 10 between the two groups, between the intervention group and the placebo group. Okay, so that's where this 10 squared comes from. If you carry out all these calculations, you wind up with a number 35.28. So study subjects have to be whole numbers, so that number needs to be rounded up to 36. So at the end of the day, you would need N equals 36 participants per group, or if we wanted the total, we would need to multiply that by 2, and that would give us 72 total participants. Alright, so that's example 1. Alright, what about example 2? So for example 2, researchers are going to do another randomized controlled trial, and they want to know if a drug reduces 5-year mortality in cancer patients. Okay, so the outcome here is alive or dead at year 5. Okay, so that's an event type of outcome. So we're going to be, in this situation, interested in the proportion of people who are still alive at year 5 between the treatment group and the control group. Okay, and hopefully the treatment group, if it has an effect, you would have more individuals or a higher proportion of individuals alive at year 5 versus the control group. Okay, in this study, from pilot data, they expect that the survival, or the proportion of people surviving in the treatment group, is going to be 60%, or 0.6, and the proportion of people surviving in the control group or the placebo group is half, so 0.5. All right. If you recall from some previous lectures ago, this p bar would be your combined estimate of these two proportions, and it would essentially just be the average of those two. So if we averaged 0.6 and 0.5, we would get 0.55, and if I go back a couple slides, that's this p bar that you see here in the formula. Okay. Alright, so we've got p bar, and they want to do a two-tailed test with alpha at 0.05. Again, that's kind of the standard. They want to have 80% power. Again, that means beta is 0.2, to detect a difference of 0.1. Okay, Where does the 0.1 come from? Well, that's just the difference in the survival rates between these two groups. So they want to have an 80% chance that they're going to call this significant. Okay. So if we look at the formula, it looks very similar. The only difference is this estimate of the sample variance. So this S squared piece, and if you remember, it kind of looks similar to some of the things when we were talking about a pooled estimate of the variance for two proportions. Okay, so that's here. So the formula looks similar, but there's one component that looks kind of different. All right, everything else is the same. So we've got this Z sub C, and again, if our alpha is 0.05, that winds up being 1.96. Okay, we've still got this Z sub beta, and if we want to have 80% power, then that number winds up being 0.84, just like in the previous example. So I'll take some of this away. This 2 is just part of the formula, and this is p bar, and this is 1 minus p bar. All right, and finally, in the denominator, we have this observed difference that we want to call significant, which was 0.1 squared. All right, so if we plug everything in, all the numbers in, then we wind up getting 388. So our n would be 388, and if we wanted to calculate the total number of participants, we would need to multiply that by 2. All right, so that could be quite a large study, especially if you're talking about following these individuals for 5 years. I mean, you have to assess their 5-year mortality, so you would at least need to get back in touch with these individuals at year 5 to determine if they're alive or not. All right, well, what would happen if we just made a slight adjustment to what we expect? So what if we thought that the drug was going to actually be more effective? So instead of, say, 60% of individuals surviving in the treatment group, what if it was more like 70% of individuals surviving in the treatment group and still maintaining a 50% survival in the control group? How's this going to change the calculation? Well, intuitively, you should already be guessing that, hey, this is a larger difference, so it should require less subjects in order to call this difference significant, right? In order for me to reach statistical significance. Okay, and that turns out to be the case. So if we just repeat this sample size calculation, everything looks the same, except now we've got a slightly different p-bar and 1 minus p-bar. So you would just take the average of 0.7 and 0.5 in order to figure that out. And we have a slightly different thing down here in the denominator. So the difference is no longer 0.1, it's actually 0.2. So we have 0.2 squared. All right, and if we carry out this calculation, then at the end of the day, what we wind up with is n equals 94. So a significant reduction in the number of individuals required to detect this difference of 0.2 versus 0.1. So we need 94 participants per group, or a total of 188 participants. Another important topic I want to talk about in this lecture is this so-called randomization. And randomization is a critical component of what's called a randomized control trial. So RCTs is how I've abbreviated it here, and RCTs are a standard in clinical research. So they're really one of the most important types of evidence in order to make conclusions about things. Okay, and randomization, or RCTs, typically requires that subjects are randomly allocated into a treatment or control group. Okay, so randomization is important for achieving internal validity because it reduces the chance of bias. It actually reduces the chance of confounding as well. Okay, so one of these is this so-called selection bias, and these two bullet points kind of illustrate how randomization can help avoid this. So what is this selection bias? So what if sickest patients were to primarily choose the treatment? Or what if health conscious study participants are more likely to choose a healthy dietary intervention. So in this first bullet, would it really be fair to compare the health outcomes between these two groups? If the sickest patients chose the treatment, they're more likely to have worse baseline health outcomes in the treatment group, just because the sickest patients chose the treatment group. For the second bullet, it wouldn't be fair to make the comparison, because it's likely that individuals in the healthy dietary intervention group are in fact health conscious and more likely to have better health outcomes than in, say, a group of people who didn't want to choose the healthy dietary intervention. So randomization is a really important tool in order to avoid this so-called confounding. So confounding is basically where you have certain variables that are associated with both your independent variable, in this case would be treatment versus placebo, and your outcome variable, so your dependent variable. Okay, if you have confounding, then it's kind of hard to separate and isolate just the effect of the independent variable that you're interested in. So in this case, treatment versus placebo. Okay, so randomization is typically carried out with a computer-generated random number in software. And the important point is to keep human preferences from influencing the randomization process. So using software or something like that can help alleviate that. Another way to keep human preferences from influencing the randomization process or the treatment allocation process is to do this so-called blinding, which I have here. So blinding study participants would be, for instance, given a placebo that looks and tastes and smells exactly like the treatment does, and another level of blinding. So this first bullet would describe one level of blinding where the study participants are blinded, so they don't know whether or not they got the placebo or the treatment. Another level of blinding would be this blinding where the individuals who are dispensing the treatment don't know whether they're dispensing a placebo pill or a treatment pill. And if you do both of these, this is the so-called double blinding, so that you have a double blind study. Okay, so there are several methods for randomization. It's not too terribly important to know all the mechanics of these, but I'll just talk about a couple of them so you can have these crossover designs. So for instance, some patients get the placebo first and then they get an intervention, or vice versa. Okay, so there's some type of sequence, and the sequence is actually randomly assigned to individuals. You can have this simple random allocation, so subjects are just randomly assigned to placebo or treatment. And the only problem with this simple random allocation is you're really not guaranteed that you're going to have an equal number of subjects in the placebo or the treatment groups. On the other hand, this block randomization guarantees that you have an equal number of subjects assigned to a placebo and the treatment group. Okay, so you essentially would do the randomization, for instance, by pairs if you had two groups. This systematic allocation works in such a way so as the first patient would be randomly assigned to a group, and then the subsequent patients would be assigned in an alternating fashion. So the first person who arrived at the site or clinic would say be assigned to placebo, and then the next patient that arrived would be assigned to the treatment, and the next patient would be assigned back to the placebo, and periodically in that alternating way. The only thing you have to watch out for here is if you have some type of periodicity effect. So for instance, if your morning people are always assigned to, say, the treatment group, then there may be differences, in subjects that aren't allocated properly between the two groups. So if you wanted to solve that kind of problem, what you could do is on the next day you could start with, say, the treatment group as your first assignment group, and alternate that way. Okay, so now I want to talk about this really important topic multiple hypothesis testing, and we've kind of touched on it a little bit in the last lecture when we were talking about ANOVA and how do you do post hoc analysis in ANOVA. So for instance, if you remember, whenever we were looking at an ANOVA, we had more than two groups, and if we rejected the null hypothesis of an ANOVA, then we would go in and do individual pairwise tests to see exactly which means are different from each other. Okay, so one of the problems today is that there's so much data and so many data sets and these big large national databases and data sets that researchers have a tendency to try to look at everything possible. So they try to assess many associations between all the variables. Okay, and data fishing or data dredging, sometimes you'll see both or either of these. So that typically is used to describe analyses where you don't necessarily have hypotheses a priori. So you're really just fishing to see if anything's going on in the data. Okay, this kind of analysis is appropriate as long as the researchers use the results really as hypothesis generating, okay, instead of hypothesis testing. So if you're doing analysis this way and you don't start out with some set of hypotheses that you then go and look at the data to test, then you really shouldn't be using these kinds of analyses as hypothesis testing. They should generate hypotheses, and then subsequent data should be collected to actually confirm, the hypotheses that were generated as a result of this data fishing. Okay, so the important point is for everybody to keep in mind is that researchers should keep in mind that hypothesis generation and hypothesis testing should be performed on different data sets, and this is critical. Okay, there are a lot of false positives out in the literature. We have a lot of, every day you see something in the news where a researcher has looked at some association and found that coffee and pancreatic cancer are related because they've done an analysis. And this is actually an example that was illustrated in your book, and it turns out that in fact when they did subsequent analyses, they couldn't repeat this statistically significant association that they found there. So no wonder the public's confused about what to do when every day of the week there's a new study out showing some association between so and so and so and so. Okay. So why is this multiple hypothesis testing a problem? Well, consider that you've got a data set with 10 variables, and the researcher wants to know whether there are associations between these 10 variables. Okay, so that would be bivariate analyses. So he or she would be interested in which variables are associated with each other. So in order to carry out that kind of analysis, you would have to look at all the ways that you can choose two variables to compare out of this list of 10 variables. So it turns out that would lead to 45 different associations that you would be trying to test. So 10 choose 2. You don't have to memorize this or anything like that, but just know that if you want to choose 2 from 10, that would give you 45 different analyses that you would have to do. So if you set your alpha to be 0.05 for each of these tests, then you should expect that if you're doing 45 of these tests, and each test you have a 0.05 chance of committing a type 1 error, then you should expect approximately 2 of these false positives from your analyses. So on average, you would see 2 false positives. Okay. So in other words, our experiment-wise chance of committing false positives is actually higher than our individual level. Okay. So anytime you do multiple hypothesis testing like this, this is what potentially can happen. You have a much higher experiment-wise error rate than these individual tests. So how do you account for that? How do you adjust for that? Well, probably the most general way to do that is this so-called Bonferroni adjustment, which I have in bullet 1. And this Bonferroni adjustment is essentially a way to correct for multiple hypothesis testing in very general situations. But the only point that I'll point out is it's conservative, but that's not necessarily a bad thing. There are way too many false positives in the literature, so there's nothing wrong with being a little conservative with the analyses and the decisions that you make from data analysis. So how do you do it? How would you carry out the Bonferroni adjustment? Well, it's very simple. You would essentially just divide your alpha. So if you want an overall alpha of, say, 0.05, so you want your overall error rate, so you want your overall probability of a type 1 error to be 0.05, then you would just divide this by the number of tests that you're performing. And only p-values that are less than this new adjusted alpha, I should probably call it alpha star. So alpha star would be 0.05 divided by the number of tests you're doing. Okay, so only p-values that are less than this new adjusted alpha star would you then call significant. Okay, so other methods exist. For instance, post hoc analysis for ANOVA, this so-called Tukey, Chaffee's method, etc. But these are usually specific to certain situations. Okay, so they wouldn't be applicable to just general analyses. But with this Bonferroni adjustment, it doesn't matter which individual analyses you were doing. So you could do 10 chi-squareds, and then you could do, say, 10 t-tests. And if you did this Bonferroni adjustment, you would still be guaranteed an overall alpha rate of whatever your desired rate would be. It doesn't matter what the individual tests are. Okay, so that's why I have this bullet here. The Bonferroni correction works in general. Okay, so conclusions. In this lecture, we've discussed important topics in the application of biostatistics. So the sample size determination is one of the most important ones. This randomization is essentially a very important tool used in randomized controlled trials. And remember, randomized controlled trials are essentially the gold standard for evidence for us for clinical decisions. And the last thing we talked about was adjusting for this multiple hypothesis testing. This is probably one of the most neglected topics, and it's a shame because we have so many false positives in the literature, so many false findings that can't be replicated, that people really need to pay attention to this multiple hypothesis testing, especially now that we're in the era of big data and you can look at 10 million different associations, and if you do 10 million different comparisons, then you're going to have a huge number of false positives. So that's not good for the literature. It's not good for the public. So just be mindful of that. Okay, in the next lecture we're going to talk about multivariable analyses. And for multivariable analyses, it's going to allow us to control for multiple independent variables. So we're going to be able to isolate the effect of one independent variable while we are controlling for potentially multiple other independent variables. Thank you.